In this video, we'll take a look at how inverses and logs can work together on the same problem. Let's look at number 15 here, 15a. So we have 2 to the power of log base 2 of 8. So one thing that we see here is that the log base 2 of 8, it's kind of its own thing. And if I just set that equal to x, because I just want to say that's some value, then that's basically saying 2 to the x is equal to 8, or that x value is then going to be 3. So what we're saying here then is really 2 to the power of 3, because we have the 2 there, and then it's to the power of 3. So 2 to the third will just give us 8. As we take a look at number 15b, we can do the same thing. We can say log base 5 of 25, what's that equal to? So we have 5 to the x is 25, or that value is just 2. So this entire thing in green is just 2, so we have 5 squared, which is 25. And similarly, okay, so now we need to figure out what log base 3 of x is. Well, based on the two examples we've just done here, maybe you can see some pattern emerging here. Hopefully what you're seeing is that if you have 2 to the power of log 2, because they are inverses of each other, they end up just canceling each other out. 5 to the power of log base 5, again, they're inverses of each other, so therefore they cancel each other out. You're left with 25. Same thing here, 3 to the log base 3, they cancel out, so you should see that they are left with just the value of x. Let's compare that inverse relationship in number 16. If f of x is 3 to the x, what is f inverse of x? Well, if you recall in our inverse unit, if f of x is the same thing as y, and then to find its inverse, you switch x and y, and then solve for y. The way that we solve for y is to remove this exponential. You can log both sides. And then not only that, but because you have a log with an exponent there, you can actually bring that y value up to the front as a coefficient. And then we want to solve for y, so we divide both sides by log 3. And so we get that y is equal to, now one thing you want to remember is that we do have a change of base formula, where if you have log x over log 3, that's the same thing as saying log base 3 of x. And one more step, one final step, remember to convert that y back into f inverse of x. So the f inverse of x is log base 3 of x. Okay, so then what we're going to do now is find f of f inverse of x, which means f, our outermost function, is 3 to the x, right? F of x is 3 to the x. So we're going to say f of f inverse of x is saying 3 to the power of whatever that x value is, which is the inverse. That's going to be log base 3 of x. Oh, and that brings us back to scenario C, and those cancel out. And you can see that we do get x, showing that they are inverses of each other. All right, let's go on to number 18. Solve without using your calculator. So if I just do the loop trick again, I have 4 to the 1.5 is equal to x. 1.5 is the equivalent value of 3 over 2. And so if I think about 3 over 2 into two parts, let's say 1/2 to the third power, then I can think of the 4 to the 1/2 right here, right? That's going to be 4 to the 1/2, and then that is to the third power. And 4 to the 1/2, we know that that is the value of 2. Okay, so we have 2 to the third, and then therefore we get 8. Let's take a look at number 20. Find the decibel level for each. The sound decibel level of I, the intensity, is given as 10 log I. That's the intensity of the sound. And I sub 0 is the initial intensity. So the average car going 70 kilometers per hour is given by I equals 10 to the power of 6.8 times I sub 0. So if we just kind of fill in the missing information, we know that the sound decibel level is given by our formula, 10 log, and then we need to just plug in the I value. Here's our I value, which is 10 to the 6.8 I sub 0 divided by I sub 0. And you see here the I sub 0's end up just canceling each other out. So what we have now is 10 log 10 to the 6.8, just like that. Okay. And then hopefully one thing you're also seeing here is that because it's technically a base 10, and we do have an exponent there, we can actually bring that exponent down. So we have 10 times 6.8 times log base 10 of 10, and that is just the equivalent value of 1. So you really just have 10 times 6.8, or that is 68 decibels. We call that dB. You see lowercase d, uppercase b. 68 decibels. Let's go on to the next page. So now we're going to just incorporate the logs and exponentials together. Now we're going to be solving equations. Just remember that inverse relationship that we had just stated before. So if I have a log, remember that logs typically use the loop trick where we're going to say 2 to the third is equal to 2x plus 1. And then at that point you just solve. So we get 8 equals 2x plus 1. So we'll get, oops, not 9. We'll get 7 is equal to 2x, or x is 7 over 2. Okay. Let's try another one. Let's do letter F. Let's do that one. So this one, loop trick would not actually help in solving this, because if you do the loop trick, you'll end up getting the x value in the exponent, and that's not what we want. Instead, if you actually look at the log, you actually do see that this is a value you can get already. Right, 6 to the x equals 36, so that x value is 2. So log base 6 of 36 is 2. And then just simplifying that, you can see here it's just a pretty simple equation. You just solve for x now. So we get negative 1 equals 5x, and therefore x is negative 1/5. Okay. Let's go on to the next section. So now we're going to use logs to solve exponentials. So in the previous example, we were using exponentials to solve for logs. Now let's use logs to solve for exponentials. So let's take a look at our first case. E to the x equals 7. Now because I have a base of e, the inverse relationship of that would be to natural log both sides. So I natural log both sides like that. And then remember, if you ever have an exponent contained within that log, you can bring that down. So we get x ln e equals ln 7. And technically ln e, those are inverses of each other. They cancel out. And so what we're left with is ln of 7. Let's do letter e together. So here, just solving like a normal, typical algebra equation, first thing you want to do is work with the outermost part first. Get rid of the outermost part, which is the minus 2. And we'll get a 12 on the other side. Then keep on working towards the x value, so we need to divide by 3 now. E to the 2x plus 1 is now equal to 4. And now this is where if we need to solve for x, it's an exponent, we need to bring that exponent down, and the way we can do that is by ln'ing both sides. And we ln it because the base was e. Okay, so we ln e to the 2x plus 1 equals ln of 4. Keep in mind you want to ln because of the base e. If this were some other number, let's say this were a number like 3, then you would just have to log both sides instead. But because it is specifically the e value, that's why we are using ln. Okay. All right, so from here, remember that if you ever have an exponent, you can bring it down. So you have 2x plus 1. Technically, it's multiplied by ln of e, but we know ln of e just cancels itself out. They are inverses of each other. And so now to solve for x, you just subtract 1 on both sides. So we have ln of 4 minus 1, and then divide both sides by 2 to get finally x equals ln of 4 minus 1 all over 2. Notice how I'm putting ln 4 in parentheses, because I don't want to mistake that for you thinking that this is like ln of 4 minus 1. So it is important you are aware of what numbers are being combined together with what operations. Okay? So that's going to be our final answer. We can just leave it like that. That's going to be in its most accurate form. Once you put it into a calculator, of course, you do get rounded decimal values. All right. Let's go on to the next page. Oh, I guess that's it. Never mind.